So this kinematics problem is brought to you by the lazy pirates. Because one day there were some pirates coming back to shore. And after they arrived, the captain let everybody off of the boat and go for shore leave, except for one sailor who had been really annoying the whole time, called Shipwreck. Now Shipwreck, he gave a job to. He said, I need you to stay here. We'll give him a pirate hat. Yarr. Yeah, I know, it's not pirate. We'll give him an eye patch then. Darr. Okay, so Shipwreck had to take all the new supply of cannonballs that they had just gotten and load them onto the ship. Well, this was a crappy job. Shipwreck didn't like it, but the captain even went for his shore leave afterwards. So Shipwreck started to think, and he said, you know, that would take forever and be really heavy to get all those cannonballs up there. What if I just fire them up there? So he got one of the ship's cannons, and he noticed that the ship was rocking back and forth on the dock. And it took 1 second for it to get completely out of the way of it, and it took 1 second before it got all the way back in the way of it. And he thought, I bet if I can fire those cannonballs at just the right time, that the ship will be out of the way, the cannonball will go by, and then when the ship moves back on, it'll fall straight down and land on board the ship. So you might reckon why his name was called Shipwreck. But anyway, we're going to see if he could succeed. We know a couple of things. We know, one, that his cannon was 1 meter. Because it's 1 meter, that means all of our velocity comes out of that cannon starting 1 meter off the ground. We also know that the cannonballs that are going to come out are going to be fired at 50 meters per second. We know that the bow of the ship is 80 meters over the deck. And luckily this does take place on Earth, so we know that it's accelerated downward at little g, which is equal to a negative 9.8 meters per second squared. Okay, so we know a couple of different things. Let's just write that out a little prettier. So here we have it all nice and pretty. You can see 50 meters per second for our initial velocity. Initial displacement is 1 meter, final displacement 80, acceleration negative 9.8 meters per second squared because it goes down. And we don't know our final velocity, and we don't know our time. And unfortunately, our time is really what we need to figure out. Because if it happens in 1 second it's in the way and 1 second when it's out of the way, depending on when he fires it, it will either be in the way or it won't be in the way, depending on how much time it takes to get there. With the variables that we know and don't know, we can start thinking about which kinematic formula to use. So we don't have time and we don't have final velocity. So we're probably not going to use 3 or 1 to start with because we're going to need to get rid of one of those variables. So number 2 doesn't have final velocity and number 4 doesn't have time. Now if you look at number 2, because that would give us our result right away if we solved it for t, we can do that because we have all of the variables. But if you notice that we do have an initial velocity this time. So to do this one, since we have t and t squared, this is basically a quadratic, and most people don't like quadratics, so let's not use it. Let's go with number 4. And since we're solving this for final velocity, it also doesn't take a whole lot of algebra. If you notice, it's just already solved for final velocity, but squared. So we're going to need to move that over, which just means we take a square root. So you take a square root of both sides, and that'll do away with it there, and we'll have to figure out the rest of it. And we can rewrite it. And really at this point, I can go ahead and plug and chug. I have all of these variables, so I'm going to put all of it in, make sure I follow my order of operations, and I'm going to solve it. Let's do that. Once I plug everything in, I solve it, and I get that my final velocity is at 30.85 meters per second. Now, this does give me information, it gives me a new variable, but it doesn't solve it yet. I still need to figure out time. So that means I'm going to need to use another formula. I notice that number 1 is nice and short, plus if I have the final and initial velocity and acceleration, it only has one variable for t for time. So let's use number 1 now to figure out time. So now that I have my first formula, I need to solve it for time. And I'm going to start by subtracting VI from both sides because that's going to cancel it out over here and allow me to move it over and get it away from the time. After that, all I have to do is divide by acceleration on both sides, and I'll cancel out acceleration on my side with the t, and I get my equation now solved for time. So now that it's solved for time, I just plug and chug, putting all of my stuff in, all of my variables in for my variable formula, and I'm going to get that the time is 1.95 seconds or thereabout. So that would actually be my answer to this question. And here's the thought. If he fired it when it was away, then it would have already moved back because it would have only been safe from 0 to 1 seconds. But if he fired it when it was already in front of it, then it would be safe. So if he did this first time, you can guess that he would know when to fire it, and it might land, it might not. If you want extra credit, we could make this more difficult by trying to predict where it will be on the way back and if the ship will actually be over top of it or not for it to land on the deck. However, I will go ahead and tell you that if you calculate that velocity out, that 30.85 meters per second, it's almost 70 miles per hour. So we might destroy the ship either way. It might end up blowing up. Anyway, there's just one more thing I wanted to look at, because remember, I told you can do all of it with number 2. You just have to use the quadratic equation. I'll prove that I get the same answer real quick. So if I take equation 2, the first thing I want to do is make it equal 0. So that means I'm actually going to move df to the other side with everything else. So I need to subtract df from both sides. Now, oddly enough, that I have it equaling 0, I want to go ahead and plug in everything I know so that I can get this looking more like a quadratic equation. So let's do that. Now I'm going to go ahead and calculate these, and I'm going to rearrange this just so I have t squared, t, and then a regular number at the side, because that's how most quadratic equations are set up. And in this form, you should be able to see this is my a, this is my b, and this is my c for the quadratic equation. And so this is the quadratic equation, if you don't remember. They say x, we're going to solve for time, but x is fine, it's just a variable. Negative b plus or minus the square root of b squared minus 4 times a times c, all divided by 2a. So really, we can just take this for a, this for b, this for c, and plug it into that formula. And that's exactly what we're going to do, and we will solve for time. So after I put everything in, it's just a matter of making sure that I put it in my calculator correctly. And I'll actually get 2 values for t. So I'll get that t, because it is plus or minus up here, by the way. So I'll get 2 values for t, plus or minus. Gives us 1 is 1.95 seconds when we do it with the positive, or 8.25 seconds, which doesn't really make sense when we do it with the negative, because that would be way past that if it's moving at 50 meters per second. So it's not really realistic that it would take 8-some seconds just to go up 80 meters if it's moving more than 10 meters a second. Anyway, so that way you can see we got the exact same answer that we got before, We just had to use the quadratic equation. So yes, you can do both. If you're wondering about our old friend Shipwreck, he did indeed live up to his name because he didn't even calculate, he didn't even measure, he just fired, and guess what? He destroyed the ship. So Captain's gonna be ticked.